Hi, my name is Hans Ivar Skjelbred. I'm a researcher at Sintef Energy Research, and I will tell you about a very exciting project I've been working on for the last 2 years. The project is called Twinlab, and the project manager has been my colleague Ingrid Wilberg, and it is financed by the FMI Hydrosen. It has been working through 2 phases of the project, and we will now present both the idea behind the project, the first phase development, and what we have been doing in the second phase. So the idea comes from that by digitalization we can achieve the goals of research faster and also facilitate good collaboration between researchers in different domains. So in the FMI Hydrosen, we have researchers doing both hydrology and catchment modeling, tunnel system modeling, dam modeling, turbine and generator modeling, and also looking at the environmental side in the downstream rivers of hydropower plants. So we wanted to make a platform where the different researchers could work together with models for different parts of the hydropower water courses. And the way we model them is by using digital twins, and that's where the name Twinlab comes from. It's a laboratory where we can work with digital twins. So when we looked at what are the basics that we have, what are the building blocks that we want to use, we saw that we have a lot of data available from our hydropower laboratory here in Trondheim, and a lot of different sensors that are listed here on the side of the screen. And there are also some plants in Norway that have installed sensors that can be made available for research. And in particular, there's a plant called Grunn OE from Skagerrak Energy, which has been very important for this project to test our ideas on. So we see the green side here, we have the operational data sets, the lab data sets from both batch measurements and live measurements. Those are the inputs on the data side. And when you work with digitalization, you need a lot of data. So that's a very important part. On the other side of the figure, we have the methods, and they can come from different sources as well, such as research projects, third-party libraries, and master's and PhD theses. Traditionally, these have been developed without a lot of coordination in the programming language and the interfaces, but we wanted to do something to fix that, so it's easier to compare different methods and build on previous work. So the blue box in the middle is what we wanted to make in Twinlab, which is a collaboration platform with both a safe and robust way of handling data and access and interfaces for all of these components. So the next step was to look at the technology stack we want to use. And here we can see that in the middle of the figure we have Python as a language that binds everything together. It's a very popular language, high level. Most students and professionals have some experience with it, and it's easy to learn by online tutorials. And then we have the data that comes from different sources here on the right hand of the figure. A lot of data from the power plant and also from lab sensors is sent via the OPC protocol. It can be mapped directly to the Python code from that, or it can go through an online cloud storage like Azure or InfluxDB. Systems like OCSoft also has the possibility to have plugins and interfaces towards solutions developed in a system like Twinlab. On the other side, we see the typical research software that is used to make dynamic models or digital twins of a physical part of the hydropower system. Simulink, LabVIEW, C++, OpenModelica, or Modelica itself are all popular tools. And The common linking between these languages and the Python core is the FMI, or Functional Mock-up Interface, which is a general way of wrapping dynamic models and interfacing them towards a common programming language. And then we can achieve this common simulation part that simulates a whole system built up of different components in one language. And yeah, there is an example of Plotly here as a visualization library, but there are many ways to visualize results in Python as well. So when this was in place, and we have made it work in the first phase of the Twinlab project, we wanted to take the next step in part 2 of the Twinlab project and make it available for online live collection of data from operational hydropower plants. So then we introduced this connection to Azure Event Hubs. And as I mentioned, Skagerrak Energi has provided their Grunnøy research unit as a source for data for this project. And we have agreed with them what requirements regarding security and scalability in the solutions for transferring data that are necessary. And that is one important outcome of the project itself, kind of what is needed in terms of data, both frequency and quality, and security when it comes to digitalization. And by closing this whole loop of gathering data and simulating it, using it in simulations, we can give a lot of answers to those questions. So this Azure Event Hubs with setting up proper event receivers in the Twinlab architecture, we have achieved a live data stream from the Grunnøy power plant. And then we have seen that a lot of students want to use this Twinlab and also research projects. So we have built up a scalable architecture on top of the Azure platform for Microsoft. We are using Kubernetes and Docker to make it scalable. So when many users log on, we will spin up new virtual machines for them. And Jupyter Hub as an interface where everyone can work in a version-controlled environment with good privacy of data and also a secure administration of the users and what they have access to. So all in all, this has become a scalable architecture. And then the final question was, okay, what are the use cases that it could help to solve? So in this second part of the project, we have titled it Accelerating Digitalization of Hydropower Research. We have had several cross-domain tasks that we have tested out and are currently testing out by the data stream and the Twinlab platform. So the first one, industry live data, that's what I just have described, how to capture data in an online platform outside the network of the plant operator. The second one is real-time efficiency estimation that we can build on top of the live data that we have. And yeah, it could be a simpler way to measure the efficiency than installing flow sensors online for, in the plant, for instance. Turbine damaging modeling, that's something we're working on. Make a digital twin of the turbine to see how the actual operation of the plant will affect the lifetime, remaining lifetime and the damage of the turbine. The online testing of FCR requirements, that's a connection to another project that is called Freki, where we take this live data we have and see if we are able to make the required calculations that Statnett requires, the transmission system operator in Norway, for qualifying a plant for delivering primary reserve to the grid. Then the second to last one is the shark bite, where this is a data measurement that has been made on the laboratory in Trondheim. In the turbine, there was cut out a part of one blade, and while the cut was getting bigger and bigger, there were done several measurements to see how large the damage had to be before we could actually detect that there was a damage there. And there's also a goal to see if artificial intelligence, AI, can find it faster than we could with traditional methods. The final is the river digital twin, where we have been building models using other systems for modeling river and water systems. And we have been looking at a different time scale there. There's a very short time scale what happens inside the power plant, but the outside propagation of water and the environmental consequences has a slower time scale. So it's kind of connecting phenomena on different time scales. That has been one of the challenges here as well. And this is an introductory video to the overall idea of the project, but several of these topics have individual videos that describe in more detail what has been going on within each of these tasks. The common results that we have the goal to achieve with this project is to improve the workflow when developing algorithms, so they're done in a professional way in a robust environment. Verification of algorithms, so we can test them against other versions or previous versions of similar algorithms, and also lower the threshold for taking research into operation. Since we are now working on a live data stream, the models we make here might be transferred to the plant operator, so maybe the real-time efficiency estimation can be put in operation within their hydropower scheduling process. So we believe a lot of these results have been achieved, and the next step for Twinlab will be to have even closer cooperation with the industry to identify more cases that give real value in the everyday operation of the system as well. So then I just want to thank Hydrosen again for supporting this project, and we are excited to see what it might bring in the future. Thank you for watching and listening.